Okay, so last class we looked at the input impedance of the passive mixer. So couple of things, the important things to remember, because the passive mixer is time variant, the input impedance looks different whether you drive it with a voltage or a current. The second thing is, in reality, the way you define this input impedance is slightly different for this mixer. Okay, normally if you have a linear circuit, linear time invariant circuit, you can use either the Thevenin or the Norton equivalent. Also, you have a particular frequency component in the input. Your current drawn by the system, by the circuit you are driving, has the same frequency component. Right? In this particular case, what happens is you are driving it maybe with a single frequency or a narrow band of frequencies. The output can have infinite number of frequencies because the system is time variant. Okay, so we define the input impedance in a very specific way. We said we are going to talk about it as if we are interested only in the frequency component, only in a narrow band of frequencies that we are driving with. The reason for this is simple. This passive mixer may be driven by let us say a low noise amplifier or a low noise transconductance amplifier, which will normally be a narrow band circuit. Maybe the LNA has a tuned load, and this passive mixer is actually loading that tuned load. That is a possibility, and therefore we are interested only in a narrow band of frequencies in terms of what current is drawn by this network. And that is also straightforward. We use the same way of analyzing it as we did for the original conversion gain. And we split it into two components, the track and the hold. And we figured out for three different cases, you will have three different kinds of impedances. And similarly, if you had a current mode passive mixer, the input impedance is now defined as Zn equals Vin by In. So there are different ways. So if you are actually applying a voltage, you actually find out your input current has many frequencies. You take the frequency of interest and calculate V by I, that gives you the input impedance. In the case of the current driven passive mode, you actually drive an input current, you measure the voltage across it. For that at that particular voltage, you can define the input impedance or input admittance. So you find out the voltage developed across the input terminals at that frequency, which will be different. Okay, so we saw that in the case of the current mode mixer, what happens is, if you have a baseband impedance which is has some kind of frequency behavior, the same frequency behavior is actually translated to the output to the input terminals. Okay, so if you have a low pass filter, for example, that gets transformed into something which looks like a band pass response, and this is quite often useful in many different kinds of circuits. So finally, we said as far as the LO swing is concerned, we initially started off with 50% duty cycle. The ideal case would be if you had an impulse sampling, which would give you a very large conversion gain. However, what is easily generatable is the 25% duty cycle. Okay, because generating a small set of narrow pulses repeatably is very difficult, and therefore we choose to just design a 25% duty cycle LO waveform, which will give you better conversion gain, 3 dB more conversion gain than your 50% duty cycle circuit. So in today's class, we'll quickly look at how you analyze the passive mixer for noise, and I'll probably not go through it in a lot of detail, maybe spend maybe 15-20 minutes on that, and then we'll move on to other things. So how do you imagine you will do passive mixer noise analysis? So now that you have done the conversion gain analysis, input impedance analysis, how would you do noise analysis? So rather, what are we interested in finding? When you do noise analysis, what do we normally do? We want to find out the input referred noise of the system, right? That will help us calculate the noise figure or anything else we want to about the circuit. How do you calculate the input referred noise of any system? First, we need to find out the noise sources and calculate how that noise goes to the output, divided by the conversion gain, divided by the gain of the circuit, and then we find the input referred noise. We will follow the same procedure here because we already know the conversion gain of the mixer, so it is easy to find out the conversion gain to the output. What are the noise sources in the mixer? The MOSFETs, okay. What else? LO may be noisy, but LO noise we'll ignore for now. Okay, so the MOSFET really may be noisy, right? If you assume you have an ideal LO signal, really the only source of noise here is the MOSFET because the output is a capacitive load, or maybe if you have a current mode driving into a virtual node, that is even better, right? You may have the input referred noise of the amplifier, which you can analyze in a different way. So, what kind of noise do the MOSFETs add? Thermal noise, flicker noise, okay? So, what kind of flicker noise do you expect from the MOSFET? Do you expect flicker noise from the MOSFET? Whether the mixer is upconverting or not, right? Okay, so that is in the case of an active mixer. We have seen that in the case of an upconverting mixer, the flicker noise is a problem. In the case of a downconverting mixer, flicker noise is not a big problem. When does flicker noise usually present itself? In any circuit, when does flicker noise present itself? Obviously, you need to have obviously a junction between two different materials through which current is not passing through the junction, but current is actually passing laterally between along the interface between two materials. If it is actually passing through something like a PN junction, you will get short noise, right? But if you have current passing laterally, for example, the interface between the semiconductor and the oxide, which is the channel in the MOSFET, when you have current going through this, from experimentally, we know that the noise pass spectral density has a 1/f kind of behavior. That is what we call flicker noise. When does this happen? Normally, flicker noise presents itself when you have a DC current flowing through this transistor. Thermal noise. What kind of thermal noise is it? It's resistive thermal noise. So the passive mixer, at the end of the day, the devices are in the resistive linear region. So it acts pretty much like a resistor. So you have a resistance, maybe some resistance R on. They'll have something which looks like 4 kT R on or 2 kT R on one side of the spectrum. Okay. So what we'll do is, the simplest way to analyze this is start off from a simple, model of your passive mixer using a resistor, using the input resistance, and then figure out how this noise actually appears at the output. Okay. So first, let's look at the return to zero mixer. Okay. Maybe this is some R on. This is RL. And okay, so this is the simple model of your return to zero mixer, and you are really interested in this output noise at the VO node. Okay, so first of all, when S1 is on, what is the output noise? Forget the noise due to the source. So let us, in fact, this would be VO spot R on, let us say. Let's forget the noise due to the source right now. We are trying to find out everything from the circuit itself. When S1 is on, what is the total noise? Correct. So it will just be R on and RL in parallel. Whatever resistance that is, that will create some noise. Okay. So this will give you 4 kT into R on parallel RL. When S1 is off, what is the output noise? 4 kT RL, right? If LO has a 50% duty cycle, what will the output noise be? approximately it will be the average of these two, right? Half the time you have 4 kT RL, the other time you have 4 kT R on parallel RL. It will just be an average of these two. Now, sorry? Okay. So PON squared on the average will be 2 kT times RL plus R on parallel RL. So this is approximately the average of the two. And what is the conversion gain of this mixer? 1 over pi. We have already seen that. Okay. Two pi square kT into RL plus. Obviously, if you are trying to design a very good mixer, you would think that R on will be very small, right? If you want R on to be very small, then this will just decompose to 2 pi squared kT RL. Okay, the second term will vanish. But note that that may not really be the optimum case for input referred noise. That is the best case for conversion gain. Okay, but that may not be the optimum case for input referred noise. In fact, the actual optimum value of input referred noise is slightly different. Now we'll look at the more important case for us, which is the sampled mixer. Okay, which has a capacitive load. So the resistance of the switch is R1. So let us say this 51 was the capacitive load. We are interested in finding, okay, Vn squared R out. So the first thing we need to find out is, if you didn't have the switch, what would the output referred noise be? It will just be this Vn squared R1, but it will be shaped by the filter characteristic, right? So without switch, this is S1. So this is just Vn squared out. Okay, Vn squared out. One by 1 plus R1 C1 omega the whole squared. Okay. And what is Vn squared R1? The one, we'll look at the one-sided spectrum. It is 2 kT R1 for minus infinity to plus infinity. Normally when we say 4 kT R, that is the one-sided spectrum. From 0 to, we usually fold it over and look at twice the noise. Okay. If you have the switch, now what happens? You have two cases again, when the switch is on and when the switch is off. When the switch is on, what happens? When the switch is on, you have exactly the same. So in fact what I'll call it is, I'll call this Vn squared LPS to make it easier. This is the Vn squared of the output squared noise of the low pass filter without the switch. So with the S1, so S1 is on. Is the same as Vn squared LPF. When S1 is off, what happens? What is the noise at the output? It is the sampled noise. There is no other noise source, but the capacitance actually holds the noise which it is actually sampled before. Okay. So this is the track mode. Okay, this is the hold mode. Held noise on the capacitor. Okay. Now how do you analyze this? We can go back and do similar kind of analysis as we did for the conversion gain and input impedance, because now we have split it into the track mode and the hold mode. So in other words, you have split it into, let us say, we had two cases, something like this. And so on. This is the track mode. Okay. The hold mode may look something like this, 0, and so on. Okay. So really in the hold mode, you are just holding whatever last value was sampled. Now the important thing to remember is that unlike your conversion gain and input impedance, you can't just find out. So let us say this was VN1 and VN2. You can't just separate these two completely and just add the two at the output. The reason is, most probably there is going to be some correlation between these two, VN1 and VN2. They are going to be partially correlated. So we are going to separate into these two modes, but are partially correlated. Okay. How do you find out the correlation between VN1 and VN2? Which is why it is going to be partially correlated, because what happens is, you are not only just holding that noise, the minute you send it through this kind of switching waveform, you now have to do what you did. What did you do earlier for this hold mode? How did you analyze this hold mode? It is like sampling it with an impulse train and then convolving it with a square pulse. So the minute you do that, you have aliasing of noise from multiple frequencies. Because of that, it won't be completely correlated, it will only be partially correlated. And because you have aliasing of noise, it just won't be a simple, just finding out the noise in that portion and adding the power. You really have to find out how much noise is aliased. Yes.
So if the RC bandwidth is kind of very small.
Correct.
Kind of tight. RC time constant is very small compared to sampling.
Time constant is very small. Okay. Yes.
Whatever maybe the last value could have stored, the moment we turn it on again sampling, that will discharge very fast.
Correct. Agreed. Absolutely. So which is why you will have to consider two things. Okay. You will have to consider the noise from low frequencies versus noise from high frequencies. Okay. As he mentioned, if the RC bandwidth is very small, then what happens is if the RC time constant is very small, if the RC bandwidth is very high, what will happen is the sample value will discharge very fast. Okay. In which case you don't have to worry about that noise. So really what you have to worry about, the noise you have to worry about, is the very, very low frequency noise which doesn't discharge very fast. The components for which the RC bandwidth is significant. Those are the noise sources for which you need to think about correlation. Okay, so which is the point I was coming to. So if you want to find out the correlation portion, so you have two parts. In the track mode, you have your previous sampled value, okay, which is being held, okay, and of course this takes some time to vanish. This takes some time to discharge. Okay. Now, how long does it take to discharge? Because when you're entering sample mode, so instead of saying in track mode, when you're entering track mode, you have the previous sampled value, okay, which needs to take some time to discharge. How long does it take to discharge? What does that depend on? So let us go back here. Okay. So for example, what I am talking about is, let us say I am looking at this time instant. Okay. I am actually having this particular previous sampled value, but the minute I enter track mode, this sample value needs to discharge. Right? How long does it take to discharge? That depends on the R1 and C1 time constant. When the switch is on, do you expect that to be low or high? You expect that to be, the RC time constant to be very low. You expect that to discharge very fast, because you are going to design your switch to have a very low resistance. So therefore, this is usually negligible. This portion because the time constant is very low when the switch is on. The second correlation you need to take care of is when you enter the hold mode. Okay, and when you enter hold mode, again your noise, you really need to worry about the noise components far below FLO. Okay, and these usually remain constant during this period. Okay, during this hold period. So let us say from 0 to, we will make an approximation. Say we are interested in noise components only from 0 to maybe 1/10 of the sampling frequency. Okay, and up here at output, what is the value of this noise? 2 kTR1. So these low frequency components appear at the output. This is the extra noise we need to add in this particular region. What is the second case we need to look at? Of course, the second case we need to look at are these two things. Now that we have looked at the correlation, let me call this, I have called these VN1 and VN2. VN1 and VN2. Now I need to find out the noise in this and then add all together. Now the one thing to keep in mind is when you do the analysis for the track mode, you can no longer consider components from 0 to FLO by 10, because you have already taken it into account in the correlation process, and same thing for the hold mode also for VN2. So I'll call those things VN1 star and VN1 prime and VN2 prime. Okay, so VN1 prime I'm going to assume that you are looking at components above FLO by 10, because you have already taken this into account in section 1. So VN1 prime of T is, now this is VLPF of T, okay, times the switching waveform S of T. We have seen this, the S of T which goes from 0 to 1. And this VN1 of F is now going to be VLPF of F convolved with S of F. Okay, we have seen that S of F is nothing but, you have an impulse train with a sink envelope. We have seen this before in the previous sections. So now we are going to make an approximation that the sampling bandwidth 1 over R1C1 is much smaller than 3 omega LO. Okay, this is to make our calculation easier because we really have to consider as many components as possible. Okay, in this convolution. In this convolution, we have to consider as many components as possible. To make matters easy for us, we are just going to consider the first and third component. This is actually Vn1 prime of f and Vn1 squared prime of f. So you get the following expression. This is the first term. This is the third term. And this is Vn1 squared LPF, which is 2 kT R1 by 1 plus f the whole squared. So this is Vn1 squared LPF. This is the first and third terms of S of f, and this is because you have both positive and negative frequencies, component aliasing. Okay, you are accounting for both positive and negative frequencies. So for low output frequencies, we can arrive at an approximation for this. So normally, if the IF is very small, or if you have a direct conversion receiver, so Vn prime 1 squared is nothing but, this is the one-sided noise, 0.226 times 2 kT R1. So the third term you need to account for is in the hold mode. So this one is nothing but is your shaped noise Tn LPF of T multiplied by we have seen this before, you have to multiply with an impulse train and then convolve it with the pulse. Just convolve it with a square pulse from 0 to TLO by 2. So this particular term will give you aliasing of noise again. And this particular case, you will get aliasing of noise from plus or minus FLO, plus or minus 3 FLO, and 2 FLO, 3 FLO, and so on. Okay, you will get aliasing of noise from these terms. And if you actually find out the expression, of the alias noise, this is nothing but 2 times. I am just giving you the final expression, I am not going through this, 2 kT R1 by TLO squared. Sigma n equal to 1 to infinity, 1 over 1 plus a square n squared, where a is nothing but, okay, a is nothing but 2 pi R1 C1 FLO. So to actually find out your actual Vn2, you have to take this alias noise and multiply it by the sink envelope. So you apply the sink envelope to this alias noise, and the final expression you get KT times 1 over 4C1 FLO minus R1 by 2. Okay? So now you can find out your overall output referred noise. It comes out to be KT times 3.9 R1 plus 1 over 2C1 FLO, and what is the conversion gain, or GC squared is 1 over pi squared plus 1 over 4. So now you can find out your input referred noise. Okay, as I said, I am not going through the details, so you can look up this particular section in section 6.2.3. in Razavi's textbook. Okay, but I have pretty much given you the basic summary of what he goes through there. It is up to you to look up the details. So obviously how you go from, I have just said it's convolved with an impulse train and a square pulse. You put in the details and I have given you the results. Okay, so that is as much as we are going to see for the passive mixer. Any questions? Okay, so obviously the passive mixer, as we have seen, it can have a large noise figure, but it can also have a very good linearity. So the overall dynamic range can be higher than what you would get from an active mixer, especially if you take into account certain things, right? If you're careful with your design, you can definitely do a good job. For example, if you want to design an up conversion mixer, right? You can definitely do a decent job with a passive mixer because it has very good linearity, which is what you are interested in a transmitter. The noise figure you are really not that interested in, right? Because your signal is already very high at the input. You are generating the signal, so you don't have to worry about the noise figure. The thing you are really interested in though is, apart from your desired signal, if you are generating other components, you really have to filter them very carefully in a transmitter. Okay, so really most transmitting mixers are still active mixers, because the passive mixers do produce a lot of other components which need to be filtered out very carefully. The second reason is, you normally in a transmitter you want to get some gain. Okay, you may start off with a very low amplitude, maybe 100 millivolts, and at the end of the transmitter you may want an output power which may be several tens of milliwatts or hundreds of milliwatts. So you can't just afford to use a passive mixer which may just have a very little gain or just some loss. You may be better off designing an active mixer. Okay. However, in terms of flicker noise, the passive mixer can be much better.